All right, so what's going on, y'all? This problem is really long, but it's easy. Just you gotta know what you're doing, obviously, but I'll tell you exactly what you need to know just to make sure you don't get stuck on these. So it says assemble a stiffness matrix by superimposing the stiffness matrices of each spring. They don't give us a value for K, but they just say, hey, it's K. And then we have to find the X and Y components of deflection at node 1. So that's just U1 and V1. So, let's go ahead and get started. All right, so for 2D elements, this is the matrix, the stiffness matrix we use, right? It's C squared, cosine, this is sine, cosine times sine. This is a stiffness value. In this case, it's just K. So instead of EA over L, we're just gonna have K, right? Because it's still a force is equal to stiffness times displacement. That's all it is, right? So this problem is a little long, so I want to kind of hurry it up. But again, if you watch the other videos, you've seen that I do this table right here to help me out. It used to help me out a lot, actually. But in this case, we have 3 elements, right? 1, 2, and 3 down here. Okay, all at different angles. Same stiffness, so that makes it easier, but check this out. I like to do this for every element so you can kind of see what's going on. We'll do it up there. I don't know how much space I'll need, but point is we want to find theta, right? We want to find the cosine of that theta. Let's go down again. We're going to find the sine of that theta. We are going to find cosine squared. We are going to find sine squared. And finally, we're going to find cosine times sine. Okay, and we're going to do that for every element. So in this case, element 1. And we're going to, let's go ahead and do this, right? Doing the best I can to stay neat. 2 and 3, that's it. So we're going to bring this down all the way here. And I suggest you do this because, well, for one, you're going to need to, right, for every element eventually, but it helps you stay organized. You won't mess up, just FYI. So element 1, 2, and 3. Element 1, again, we take the angle from the x-axis, the positive x-axis. So this is 180, a straight line, right? So that means up to here, this is 135. 135 degrees. Again, it's this angle. So it's 135 degrees. You take the cosine of that angle, you're going to get negative radical 2 over 2. And I know we did a lot of things right here, right? But we only care about these 3. But you need all this stuff to get here. It's like a step. First you get the element, then you get the theta, then the cosine, and the sine, then blah, blah, blah. So you do that. That's cosine of that angle, right? 135. Sine of that angle is radical 2 over 2. Okay. Cosine squared of that angle is positive 1/2. Sine squared, it's positive 1/2, and cosine times sine, it's negative 1/2. Now we do the second element, right? This one's 180 degrees now. We're going all the way here. So it's not 45. Don't let these things confuse you. They're just reference points, but you got to do it with respect to the x-axis. So that's 180 degrees. Cosine of that angle is negative 1. Sine of 180 is 0. Cosine squared is 1. Sine squared is 0. And then cosine times sine is 0. And finally, for element 3, this angle now from the positive x-axis, that angle is 225. And right, we take the cosine of that angle, that's negative radical 2 over 2. Negative radical 2 over 2. We got positive 1/2 for cosine squared. Sine squared is again positive 1/2. And then finally, cosine times sine, that's another positive 1/2. So cool, we got all the 3 values we needed to assemble the matrix, the little matrices, right? Then we're going to superimpose those little matrices into the global stiffness matrix. So just like we've been doing previously, right, for the problems, if you've been watching the videos, it's nothing different. Step 3 now, but this problem is going to get a little crazy, just FYI. So K1 is equal to, it would have been EAL, right? But it's just stiffness, they give it K. So we'll do K. And then that's gonna be of the first element, right? We're doing the first element. So that is between nodes 1 is, right? Let me erase that right here. This is node 1 right here. And this is node 2. That's the first element. So we're doing the first element. So it's gonna be U1, V1, U2, V2. What that means, it's just the X, Y at node 1. X coordinate, Y coordinate. X coordinate in node 2, Y coordinate in node 2. And that's it. U1, V1, U2, V2. And again, I choose 1 and 2 because it's between nodes 1 and 2, okay? Just make sure you're using the correct nodes. All right. So for the first one, it's cosine squared. Again, we're on the first element, so it's half, okay? But what I'm gonna do is I'm gonna factor out that half, so it could just be 1, okay? So I'm gonna divide K over 2. Now everything's gonna be nice, just ones, because everything up here is ones, right? So it would have been half, but we factored out the half, so that's just 1. C times S is negative right there, -1. Again, we factored out the 2. Negative C squared, it's -1. And then negative CS, that will be a positive 1. Again, the negatives cancel out. Next one. S squared will go here. Sine squared right here is +1. Negative CS, that's going to be a +1. Negative S squared, that's going to be a -1. Okay. Next one, right here, C squared. That's going to be +1. That's going to be -1. I'm just plugging in, right? And I remember I factored out the half, so it could be nice ones, and this half right here is gonna make up for that. And finally, S squared, that is just 1. Now it's symmetrical, right? It says symmetrical, so we're gonna go, this -1 goes here, this -1 goes here, and this +1 goes here. Same thing, this +1 goes here, this -1 goes here, then this -1 goes here. That's the matrix for the first element. Keep it going, right? We go to K2 now. It's gonna be equal to K. We're gonna go ahead and do the matrix. Now it's between second element, right? K2. It's between nodes 1 and 3. So you got U1, V1, U3, V3. Then same thing up top, U1, V1, U3, V3. You want to be neat, okay? I'm going a little fast here, so it's not too neat, but just make sure you don't get lost. We got U1 now. Normally, I factored out the half here, right? But these are just perfect 1s and 0s, so I'm not going to factor anything out. So U1, for element 2, we got C squared right here. So it's going to start here. C squared, that's going to be 1. CS is going to be 0, okay? Negative C squared, it's -1, and then negative CS is just 0. Next one, S squared, for again element 2. I'm looking at element 2 now, so 1, 0, 0. That's all I'm looking at. So it's S squared, which is 0. It's negative CS, which is 0. And then it is negative S squared, which is 0. Okay, cool. Looks pretty simple. Next one is C squared and CS. So C squared is 1, CS is 0, so it's 1, 0. Finally, it's S squared, that is 0. And cool, so we got that one. Again, that 0 goes here, -1, right? That one goes here, and 0. These two zeros go down here, and then this 0 goes here. So we got the second one. Do the step one more time for K3. Let me write the K a little lower. Well, you know what? Let me do this. Right? So it's going to be U1, V1, U3, and V3. Make it a little bit lower. Okay, that's it. So it's K3 now, element 3. That's equal to K times the matrix. Now again, we're dealing with, I only care about these numbers, okay? This one, and this one. So I'm gonna factor out the 2 one more time, okay? So I'm gonna do it k over 2. Now I'm gonna deal with just ones. All three are positive, so anything here, it's the way it is. So it's 1. They're all ones, okay? So it's just 1, 1, negative 1, negative 1. 1, 1, negative 1, negative 1. I'm gonna close the bracket here. And again, this is, whoa. This is U4. Okay, wow. Good thing that I caught that. Between nodes 1 and 4, okay? 1 and 4. So this is U1, V1, U4, V4. Just make sure you're doing the stiffness matrix correctly, all right? Whatever element you're doing, make sure between what nodes are they in. Yeah, that's it, right? So it's 1, they're all positive, so it's 1, negative 1, negative 1. Got 1, negative 1, negative 1. 1, 1, 1, 1, and then 1, 1. So then we got, right, just symmetrical matrix, negative 1, negative 1, negative 1, negative 1, and 1. And that's it. We got all three. So now that we have all three, we could go ahead and do the global stiffness matrix. Now it's a little crazy, right? Because you're dealing with 8. It's going to be an 8 by 8 matrix. You got 4 nodes, and the x and y for each node, that's 8. 8 rows, 8 columns. So we're finally getting into FEA where this shit's getting just ridiculous. But as long as you're consistent, you'll be all right, okay? So you start with F1x, F1x, F1y. Then we got F2x, F2y. Then we got F3x, F3y, F4x, F4y. Because it's 2D now, right? And each node is gonna have a X and Y reaction. So that's why this thing is getting a little crazy. All right, now hold on. We cannot continue just yet. Usually, yeah, you'll do the huge matrix, right? It's gonna be this. It's gonna be it's U1, V1, U2, V2, U3, V3, and U4, V4. Okay? Same thing across. So it's going to be U1, V1, U2, V2, U3, V3, and U4, V4. Okay? So, oh man, it's gonna be really crazy. Now there is a shortcut. I'm not gonna lie to you. So I'm just putting the displacement vector, right? Its force is equal to kx. This is your k, right? And your x, it's just u1, v1, u2, v2, u3, v3, and then u4, v4. Whoa, man. Okay. So this already gets a little crazy. We cannot assemble this matrix unless the outside is all the same. In this case, it's k over 2, and just k. We can only add them if this is also a k over 2, or if these twos are just k's. In this case, it's easier, well, at least for me. You could multiply this 2 into all these over here, and same with this one, and you'll just have you'll have k outside, right? You'll be good. But the thing is, you're gonna have 1 half, 1 half, negative 1 half, negative 1 half. Everything's gonna be in terms of half here. I don't like dealing with fractions. That's just me. So what I'm gonna do is I'm gonna multiply everything in here by 2, and then I'm just gonna divide this by 2. So this is just gonna become a 2, negative 2, negative 2, and 2. Okay, so that's all it is. Now that I did this, I could add all the matrices together because they all share the same multiple. I don't even know what you call this, right? K over 2. So this is going to be a K over 2. And I'm going to just go ahead and, just like we did in previous videos, right? We're just going to go ahead and assemble the matrix using all the positions. Now, This is the shortcut that you're gonna have to use. It's not really a shortcut because you're expected to know it, okay? So it's not like a trick that I found. It's just the way you do this problem. You start applying the boundary conditions. This is what I'm gonna do. Boundary conditions by crossing out. I'm gonna put I don't know if I spelled this correctly. Eliminating rows and columns. Because you could go ahead and assemble the matrix by adding every single node. So anything that's U1, you gotta add it. So it's 1 here, 2 here, 1 here. This is gonna be a 4. You gotta do that for every single one. Find U4 and U3, for example, if there's any, and then just work with it that way. It's gonna be crazy if you do that. So start applying the boundary conditions before you assemble the matrix. So let's do it. The nodal displacements. U2 and V2 is fixed. They will be 0. So that's what I'm gonna do. I'm gonna cross this down, U2 and V2. 0. Same, I'm gonna do the same thing diagonally or whatever. U2 is crossed out, right? Try to be as neat as you can so you won't get mixed up. And V2 is crossed out. Okay? So that's that one. U3 and V3, same thing. They're fixed. They will never move no matter how much force you apply anywhere. So U3 and V3 is gone. So same thing, right? All right, so same thing, right? U3 and V3 are gone. Okay, so now next one. U4 and V4 will always be fixed. So U4 is gone, V4 is gone. And again, U4 is gone, V4 is gone. So everything crossed out except these 4 positions. U1, V1, U1, V1, these 4. Now it makes sense, right? U1, if you apply a force here, it's gonna move. It's not fixed anywhere, so something's gonna happen. So that's how you apply the boundary conditions. It's gonna save you a lot of time. All these are equal to 0. U2 is equal to 0, V2 is equal to 0, U3 is equal to 0, V3, U4, V4, all equal to 0. Now, I'm not gonna go ahead and erase it and plug in 0 because we're not gonna need it. That doesn't mean there's no force at these, okay? This is just, the problem is asking find the X and Y components, U1 and V1, at node 1. So yeah, U1, V1. So now we could just go ahead and focus on these two, this node, right? X and Y for node 1. Now we got 1 here. That's a U1, U1, right? U1, U1. This is a U1, V1. This is a V1, U1 we're gonna need. And then this is a V1, V1 we're gonna need. Here too, right? We're gonna need this too, U1, U1. We're gonna need V1, U1. It's a row column. We're gonna need U1, V1, and we're gonna need V1, V1. Next one, we're gonna need, again, U1, U1. We're gonna need V1, U1. We're gonna need U1, V1, and then we're gonna need V1, V1. So we just add those and then throw it in here. So all the U1s, it's 1, 2, and 1. So it's gonna be 4. Next one, it's -1. We're gonna do U1, V1 next. -1, 0, and 1. So that is 0. Next one is -1, 0, and 1. So that is 0. Then we have 1, 0, and 1. So that is 2. All right, damn. It's just long, huh? So we could apply our force condition, our boundary condition for force 2, right? That's gonna be 0 in the X direction. So 0, and then -10 in the Y direction. So we could go ahead and get the answers. I'm gonna get a new fresh piece of paper, right? Step 5. Okay, let me move it up. It's gonna be 0 is equal to 4 times U1, which is 4U1, plus 0 times V1, 0 V1. This is 0, okay? So that means u1 is equal to 0, right? Divide both sides by 4. You got your u1. Cool. Now, next one, we're going to do -10, step 6. -10. Let me move this up in case you can't see. -10 is equal to 0u1 plus 2v1, right? 0 times u1 plus 2 times v1. So this is 0. That means v1 is equal to, missed one thing, k over 2. Okay? It's all this times k over 2. Same thing here. Fortunately, it was 0 regardless. I forgot about that. Don't forget it, okay? So it's k over 2. So multiply, let's do, this is 0. So I don't even know why we included this. 2 times 2, this is kv1. So it's -10 over k. And that's your answer right there. So we got u1 is equal to 0 and v1 is equal to -10 over k. And that's it. Now, normally, once we get the u and v1s, you'll plug them in and you could solve this equation, right? There was 8 equations, 8 unknowns. These were 2 unknowns. These are 1, 2, 3, 4, 5, 6 unknowns. Yep. So 6 here and the 2 here, that's 8. And you could assemble 8 equations. So this problem is solvable, right? I'm not sure if you could see the paper, but these 6 unknowns right here, the forces, and these 2 unknowns for displacements. So you could solve this if you had the calculator. Way better, easier, way easier, right? By hand, you're gonna take a while. I doubt he's gonna make you solve this on the exam. Now, this is an exam problem, though. If he lets you use the calculator, expect to see something like this on the exam. But use this table. It's really going to help you. At the end of the day, you only care about these 3 numbers anyway. So, I mean, all this is just to get to here. You got to know the matrix, right? When you're dealing with 2D beams, bars, I guess in this case, spring assemblies, you're going to need this matrix right here. What else do I want to say? Boundary conditions. Know how to apply them, or else you were going to spend a lot of time assembling this damn matrix. You got to do every single point, and then just add them is just so damn crazy. You could do it. It's going to take time, but that's how you do it. Okay? So that's the bottom part, and then this is the top part.